Subscribe to Boring Science for sleep for new videos every day. Now, let us begin. The study of clay minerals represents one of the more quietly significant branches of earth science, a discipline in which the particles under examination are so remarkably small that they cannot be seen with the naked eye, and yet these particles, through their cumulative presence in soils, sediments, and geological formations around the world, exert an influence on agriculture, construction, ceramics, and countless other fields that is difficult to overstate. Clay, in the most general sense, refers to a naturally occurring material composed primarily of fine-grained minerals, which typically exhibit plasticity when sufficiently wetted and which harden upon drying or firing. The particle size that defines clay is generally accepted to be less than 2 micrometers in equivalent spherical diameter, a threshold that was established through decades of careful sedimentation analysis and that remains the standard in most geological and soil science classifications to this day. The formation of clay minerals is a process that unfolds over geological timescales, involving the gradual chemical weathering of silicate-bearing rocks. When feldspars, micas, and other primary minerals are exposed to water, carbon dioxide, and organic acids over periods ranging from thousands to millions of years, their crystal structures slowly break down and reorganize into the layered silicate structures that characterize clay minerals. This process, known as argillization, proceeds at rates that depend on temperature, rainfall, the composition of the parent rock, and the presence or absence of vegetation, among other factors. In tropical regions, where temperatures are consistently warm and rainfall is abundant, the weathering of rocks into clay minerals proceeds more rapidly than in arid or cold climates, where the necessary chemical reactions are slowed by the limited availability of water or the reduced kinetic energy of molecules at lower temperatures. The classification of clay minerals into distinct groups is based primarily on their crystal structure, which determines many of their physical and chemical properties. The most fundamental structural unit of clay minerals is the silica tetrahedron, in which a single silicon atom is surrounded by 4 oxygen atoms arranged at the corners of a tetrahedron. These tetrahedra link together by sharing oxygen atoms to form continuous two-dimensional sheets, known as tetrahedral sheets. The second fundamental structural unit is the alumina octahedron, in which an aluminum atom is surrounded by 6 oxygen atoms or hydroxyl groups arranged at the corners of an octahedron. These octahedra similarly link together to form continuous octahedral sheets. The manner in which these tetrahedral and octahedral sheets are stacked and bonded together determines the basic classification of clay minerals into groups, such as the kaolinite group, the smectite group, the alite group, and the chlorite group, among others. Kaolinite, perhaps the most widely recognized of all clay minerals, belongs to the 1-to-1 layer type, meaning that each layer of the mineral consists of 1 tetrahedral sheet bonded to 1 octahedral sheet. The chemical formula of kaolinite is Al2C2O5OH4, and its layers are held together by hydrogen bonds between the oxygen atoms of the tetrahedral sheet in one layer and the hydroxyl groups of the octahedral sheet in the adjacent layer. These hydrogen bonds are sufficiently strong that water molecules and other ions cannot easily penetrate between the layers, which gives kaolinite several distinctive properties. The basal spacing of kaolinite, which is the distance from the top of one layer to the top of the next, is approximately 0.72 nanometers. A measurement that has been confirmed repeatedly through X-ray diffraction studies conducted in laboratories around the world. The physical properties of kaolinite are, in many respects, a direct consequence of its crystal structure. Because the layers are held tightly together by hydrogen bonds, kaolinite has a relatively low cation exchange capacity, typically ranging from about 3 to 15 milliequivalents per 100 grams of clay. This means that kaolinite has a limited ability to attract and hold positively charged ions on its surface, a property that has significant implications for soil fertility and for the behavior of kaolinite in various industrial applications. The specific surface area of kaolinite is also relatively low, generally falling in the range of 10 to 30 square meters per gram, which is modest compared to some other clay minerals. The plasticity of kaolinite, while sufficient to make it useful in ceramics and other applications, is less pronounced than that of smectite clays, a difference that can be attributed to the lower surface area and the absence of interlayer swelling. The deposits of kaolinite that are found in various parts of the world have formed through different geological processes, and the characteristics of the kaolinite in each deposit reflect the specific conditions under which it was formed. Primary kaolin deposits, also known as residual deposits, are formed in place by the weathering of feldspar-rich rocks such as granite and arkose. In Cornwall, England, extensive deposits of primary kaolin have been mined since the mid-18th century, and the kaolin from this region has long been prized for its whiteness and purity. The kaolinization of the Cornish granites is believed to have been caused in part by hydrothermal fluids that circulated through the rock mass during and after the emplacement of the granite batholith, a process that may have begun as early as 280 million years ago during the Permian period. Secondary kaolin deposits, by contrast, are formed when kaolinite that has been weathered from its parent rock is transported by water and redeposited in sedimentary basins. The kaolin deposits of Georgia and South Carolina in the United States are notable examples of secondary deposits, and these deposits, which were laid down during the Cretaceous and Tertiary periods, contain kaolinite that has been naturally refined by the sorting action of water, resulting in material that is often remarkably pure and well crystallized. The industrial applications of kaolinite are numerous and varied, reflecting the mineral's combination of whiteness, chemical inertness, and moderate plasticity. In the paper industry, kaolinite is used extensively as both a filler and a coating pigment, where its fine particle size and plate-like morphology contribute to the smoothness, brightness, and printability of paper. The amount of kaolin used in paper production is substantial, with a single ton of coated paper requiring approximately 200 to 300 kilograms of kaolin coating. In the ceramics industry, kaolinite is the primary raw material for the production of porcelain, stoneware, and other whiteware products. When kaolinite is heated to temperatures above approximately 550 degrees Celsius, it undergoes a dehydroxylation reaction in which the hydroxyl groups are driven off as water vapor, transforming the mineral into a disordered phase known as metakaolinite. Further heating to temperatures above approximately 980 degrees Celsius causes the metakaolinite to transform into a spinel-type phase, and at temperatures above approximately 1050 degrees Celsius, the mineral begins to form mullite, a high-strength aluminosilicate that gives fired ceramic products much of their mechanical strength and thermal resistance. Turning now to the smectite group of clay minerals, one encounters a class of materials whose properties differ markedly from those of kaolinite, owing to fundamental differences in crystal structure. Smectite minerals belong to the 2-to-1 layer type, meaning that each layer consists of one octahedral sheet sandwiched between two tetrahedral sheets. The most common member of the smectite group is montmorillonite, which has the general formula Na, Ca, 0.33, Al, Mg, 2C4010, OH, 2NH2O. The layers of montmorillonite are held together by relatively weak van der Waals forces and by the electrostatic attraction of interlayer cations, which compensate for the net negative charge that arises from isomorphous substitution within the crystal lattice. Because these interlayer forces are considerably weaker than the hydrogen bonds that hold kaolinite layers together, montmorillonite has the remarkable ability to absorb water molecules and other polar substances between its layers, causing the mineral to swell significantly. The basal spacing of montmorillonite can vary from approximately 0.96 nanometers in the fully dehydrated state to more than 2.0 nanometers when the mineral is fully hydrated, and in some cases, the layers can separate completely, a phenomenon known as complete dissociation or exfoliation. The swelling behavior of montmorillonite is one of its most distinctive and consequential properties. When montmorillonite comes into contact with water, water molecules are drawn into the interlayer spaces by the hydration energy of the interlayer cations, and the mineral expands perpendicular to the layers. The extent of swelling depends on several factors, including the type of interlayer cation, the concentration of dissolved salts in the surrounding water, and the confining pressure. Sodium montmorillonite, in which sodium ions occupy the interlayer positions, exhibits the greatest degree of swelling, and it is this variety that is most commonly referred to as bentonite in industrial contexts. Calcium montmorillonite, by contrast, swells to a lesser extent because the divalent calcium ions hold the layers more tightly together than the monovalent sodium ions. The practical consequences of this swelling behavior are considerable. In civil engineering, the presence of smectite-rich soils can cause significant problems for foundations, roads, and other structures. as the cyclical swelling and shrinking of the soil in response to changes in moisture content can generate pressures sufficient to crack concrete and displace structural elements. The annual cost of damage caused by expansive soils in the United States alone has been estimated at several $billions, a figure that underscores the importance of understanding the properties of smectite minerals. The cation exchange capacity of montmorillonite is substantially higher than that of kaolinite, typically ranging from about 80 to 150 milliequivalents per 100 grams. This high cation exchange capacity is a direct consequence of the large amount of isomorphous substitution in the crystal lattice and the expansive interlayer surfaces that are accessible to cations in solution. The specific surface area of montmorillonite is also remarkably high, with values commonly reported in the range of 600 to 800 square meters per gram when both external and interlayer surfaces are considered. These properties make montmorillonite an exceptionally effective adsorbent, and the mineral finds wide application in industries ranging from oil drilling, where it is used as the primary component of drilling muds, to environmental remediation, where it is used to line landfills and to contain the spread of contaminants in soil and groundwater. The formation of montmorillonite and other smectite minerals typically requires conditions of moderate weathering intensity, where the leaching of silica from the parent material is not so extensive as to favor the formation of kaolinite. Smectite minerals are commonly found in soils and sediments derived from volcanic ash because the glassy, chemically unstable nature of volcanic ash promotes rapid alteration to smectite under appropriate conditions of drainage and climate. The bentonite deposits that are mined commercially in many parts of the world are, in most cases, the products of the alteration of volcanic ash beds that were deposited millions of years ago. The extensive bentonite deposits of Wyoming, for example, are believed to have formed from volcanic ash that was erupted from volcanoes in what is now the Yellowstone region during the Cretaceous period, approximately 70 to 100 million years ago. These deposits, which occur in beds ranging from a few centimeters to several meters in thickness, are among the most commercially important bentonite deposits in the world, and they have been mined continuously since the early 20th century. The distinction between sodium bentonite and calcium bentonite, while seemingly a minor chemical detail, has profound implications for the industrial utility of the material. Sodium bentonite, with its superior swelling capacity, is preferred for applications such as drilling muds, where the ability of the clay to form a thick, viscous suspension is essential for maintaining the stability of the borehole and for carrying cuttings to the surface. Calcium bentonite, on the other hand, is more commonly used in applications such as foundry sand bonding and as an absorbent for pet litter, where moderate swelling and good absorption capacity are desired, but extreme swelling would be counterproductive. The conversion of calcium bentonite to sodium bentonite, a process known as sodium activation, can be accomplished by treating the clay with sodium carbonate, which replaces the calcium ions in the interlayer spaces with sodium ions. This process has been practiced commercially for many decades and has greatly expanded the range of bentonite deposits that can be used for applications that require sodium bentonite properties. The rheological properties of bentonite suspensions are of particular interest in the context of drilling fluid technology. When sodium bentonite is dispersed in water at concentrations of approximately 5 to 6% by weight, it forms a colloidal suspension that exhibits thixotropic behavior, meaning that the suspension becomes less viscous when subjected to shearing forces and returns to a gel-like state when the shearing forces are removed. This thixotropic behavior is essential for the functioning of drilling muds, because the fluid must be sufficiently thin to be pumped through the drill string and back to the surface during active drilling, but it must also be sufficiently thick to suspend the drill cuttings and to prevent the settling of heavy weighting materials when circulation is stopped. The thixotropy of bentonite suspensions arises from the formation of a three-dimensional network of clay particles that is disrupted by shearing and that reforms when the suspension is at rest, a process that is governed by the balance of electrostatic and van der Waals forces between the particles. Moving beyond the smectite group, it is appropriate to consider the alite group of clay minerals, which occupies an intermediate position in many respects between kaolinite and the smectites. Alite is a 2-to-1 layer silicate, similar in basic structure to montmorillonite, but with several important differences that give it distinctly different properties. The most significant of these differences is the presence of potassium ions in the interlayer spaces, which serve to hold the layers together more firmly than the hydrated cations found in smectites. The potassium ions are particularly effective in this role because their ionic radius of approximately 0.133 nanometers is almost exactly the right size to fit into the hexagonal cavities in the tetrahedral sheets of adjacent layers, creating a strong electrostatic bond that resists the entry of water molecules. As a result, alite does not swell appreciably when exposed to water, and its basal spacing remains relatively constant at approximately 1.0 nanometers regardless of the moisture conditions. The chemical composition of alite is variable, but a representative formula might be written as K H3O Al Mg Fe2C Al Furo10 OH2 H2O, reflecting the fact that the mineral typically contains significant amounts of potassium, aluminum, magnesium, and iron, along with silicon and oxygen. The degree of substitution of aluminum for silicon in the tetrahedral sheets is generally greater in alite than in montmorillonite, which contributes to the higher layer charge that attracts the potassium ions into the interlayer spaces. The cation exchange capacity of alite is intermediate between that of kaolinite and that of montmorillonite, typically falling in the range of 10 to 40 milliequivalents per 100 grams. Similarly, the specific surface area of alite, at approximately 65 to 100 square meters per gram, is greater than that of kaolinite, but substantially less than that of montmorillonite. These intermediate properties make alite a mineral of moderate reactivity, neither as inert as kaolinite nor as active as montmorillonite. Alite is by far the most abundant clay mineral in sedimentary rocks, comprising an estimated 50 to 60% of the clay mineral content of the average shale. This abundance reflects the fact that alite is thermodynamically stable under a wide range of geological conditions, and that many other clay minerals, including smectite, tend to transform into alite over time as they are buried and subjected to elevated temperatures and pressures. The transformation of smectite to alite, known as the smectite to alite transition, is one of the most extensively studied processes in diagenetic mineralogy, and it has important implications for the petroleum industry because it occurs at the same temperatures and pressures that are associated with the generation of hydrocarbons from organic matter. The transition typically begins at temperatures of approximately 60 to 80 degrees Celsius and is essentially complete by approximately 120 to 200 degrees Celsius, depending on the availability of potassium and the duration of exposure to elevated temperatures. The process involves the gradual replacement of interlayer hydrated cations with potassium ions, accompanied by an increase in the aluminum content of the tetrahedral sheets and a reduction in the ability of the mineral to swell. The occurrence of alite in soils is also widespread, particularly in temperate and semi-arid regions where the weathering conditions favor the preservation of potassium in the clay fraction. In the Great Plains of the United States, for example, alite is commonly the dominant clay mineral in agricultural soils, and its presence contributes to the moderate fertility and good physical properties that make these soils suitable for crop production. The potassium that is held in the interlayer spaces of alite can be slowly released to the soil solution as the mineral weathers, providing a long-term source of this essential plant nutrient. However, the rate of potassium release from alite is generally slow, and in many agricultural systems, supplemental potassium fertilization is still necessary to maintain optimal crop yields. The chlorite group of clay minerals represents yet another structural type, characterized by a 2-to-1 layer structure with an additional brucite-like or gibbsite-like interlayer sheet. The general structure of chlorite can be described as an alternating sequence of a 2-to-1 layer, similar to that found in micas or alite, and an interlayer hydroxide sheet, with the two components held together by hydrogen bonds and electrostatic forces. The chemical composition of chlorite is highly variable, with magnesium, iron, and aluminum being the most common octahedral cations. A simplified formula for a magnesium-rich chlorite might be written as Mg Fe3C Al 4O10 OH 2 Mg Fe3 OH 6. Although the actual composition can vary considerably depending on the specific geological environment in which the mineral was formed. The properties of chlorite reflect its tightly bonded structure. Like alite, chlorite does not swell in the presence of water because the interlayer hydroxide sheet effectively prevents the entry of water molecules between the layers. The basal spacing of chlorite is approximately 1.4 nanometers, which is the sum of the thickness of the 2-to-1 layer and the interlayer hydroxide sheet. The cation exchange capacity of chlorite is generally low, typically less than 10 milliequivalents per 100 grams, reflecting the limited accessibility of the interlayer surfaces and the relatively low amount of isomorphous substitution compared to smectites. Chlorite is most commonly found in metamorphic rocks and in the clay fraction of sediments derived from the erosion of metamorphic terrains, and it is particularly abundant in the sediments of rivers and continental shelves that drain mountainous regions. The vermiculite group of clay minerals deserves mention as well, for it represents a structural and behavioral intermediate between the micas and the smectites. Vermiculite has a 2-to-1 layer structure similar to that of montmorillonite, but with a higher layer charge, typically in the range of 0.6 to 0.9 per formula unit, compared to 0.2 to 0.6 for montmorillonite. This higher layer charge is usually the result of greater substitution of aluminum for silicon in the tetrahedral sheets. The interlayer spaces of vermiculite are occupied by hydrated cations, most commonly magnesium, and the mineral can swell to a limited extent when exposed to water, but the degree of swelling is much less than that of sodium montmorillonite. The basal spacing of vermiculite in its natural state is approximately 1.4 nanometers, reflecting the presence of 2 layers of water molecules in the interlayer space. But this spacing can be reduced to approximately 1.0 nanometers by heating or by exchanging the interlayer cations with potassium, which causes the layers to collapse. One of the most striking properties of vermiculite is its behavior upon rapid heating, a process known as exfoliation. When vermiculite is heated quickly to temperatures of approximately 700 to 1000 degrees Celsius, the interlayer water is converted to steam so rapidly that the resulting pressure forces the layers apart, causing the mineral to expand dramatically in volume, sometimes by a factor of 15 to 30 times. The resulting expanded vermiculite is an extremely lightweight material with excellent thermal insulation properties, and it has been used extensively in the construction industry as loose-fill insulation, as a lightweight aggregate in concrete and plaster, and as a component of fireproofing materials. The major deposits of vermiculite that have been mined commercially are located in South Africa, the United States, Brazil, and Russia, with the Palabora mine in South Africa having been one of the largest sources of vermiculite in the world for many decades. The mixed-layer clay minerals represent a category of particular complexity, in which different types of clay mineral layers are interstratified within a single crystal. The most common type of mixed-layer clay is the light smectite interstratification, in which light layers and smectite layers alternate in varying proportions and with varying degrees of regularity. The description of these mixed-layer minerals requires the specification of both the types of layers present and the manner in which they are arranged, which can range from random interstratification, in which the sequence of layer types follows no discernible pattern, to ordered interstratification, in which the layers alternate in a regular, repeating sequence. The identification and characterization of mixed-layer clay minerals is accomplished primarily through X-ray diffraction analysis, using techniques that involve the comparison of experimental diffraction patterns with patterns calculated from structural models. This analysis can be technically demanding, requiring careful sample preparation and sophisticated computational methods, but it provides invaluable information about the diagenetic history of sedimentary sequences. The sepiolite and palygorskite minerals, while less commonly encountered than the layer silicate clays discussed above, possess unique structural features and properties that merit attention. Unlike the layer silicates, which have continuous two-dimensional sheets, sepiolite and palygorskite have structures that can be described as ribbons or chains of the 2-to-1 layer type, with the ribbons linked together at their edges to form a three-dimensional framework that contains channels running parallel to the fiber axis. The chemical formula of sepiolite is Mg4C6015 OH 2,6H2O, while palygorskite, also known as adipolgite, has the approximate formula Mg-Al 2C4010 OH 4H2O. The channel structure of these minerals gives them an unusually high porosity and specific surface area, and they are effective adsorbents for a variety of organic and inorganic substances. The fibrous morphology of sepiolite and palygorskite also gives them distinctive rheological properties, and suspensions of these minerals in water exhibit high viscosity at low shear rates, making them useful as thickening agents and suspending agents in applications such as drilling fluids, paints, and pharmaceutical preparations. The deposits of palygorskite in the southeastern United States, particularly in Georgia and Florida, have been mined extensively for use as absorbent materials, most notably as the active ingredient in many traditional formulations of cat litter and as an absorbent in oil spill cleanup products. The formation of these deposits is believed to have occurred during the Paleogene period, approximately 40 to 50 million years ago, when the region was covered by a shallow sea in which conditions of elevated salinity and high magnesium concentrations favored the precipitation of palygorskite from solution. The palygorskite in these deposits occurs in beds of varying thickness and purity, and the mining and processing of the material involves relatively straightforward techniques of excavation, drying, and size classification. The behavior of clay minerals in the presence of water is a subject of considerable scientific interest, not only because of its practical implications, but also because it provides insights into the fundamental nature of mineral-water interactions at the nanoscale. When a clay mineral particle is immersed in water, a diffuse double layer forms around the particle, consisting of a layer of adsorbed cations near the negatively charged surface and a more diffuse cloud of cations and anions extending outward into the solution. The thickness of this double layer depends on the charge density of the clay surface, the valence and concentration of the ions in solution, and the dielectric constant of the water, and it can be calculated using the Gowey-Chapman theory, which was developed independently by Louis George Gowey in 1910 and David Leonard Chapman in 1913. The double layer has a profound influence on the colloidal behavior of clay suspensions, governing phenomena such as flocculation and dispersion, sedimentation rate, and the rheological properties of concentrated suspensions. The phenomenon of flocculation, in which individual clay particles aggregate into larger clusters or flocks, is of particular importance in many industrial and environmental contexts. Flocculation occurs when the repulsive forces between clay particles, which arise primarily from the overlap of their diffuse double layers, are overcome by the attractive van der Waals forces between the particles. The balance between these repulsive and attractive forces is described by the DLVO theory, named after Boris Durkheim, Lev Landau, Evert Verwey, and Theodor Overbeek, who developed the theory independently in the 1940s. According to the DLVO theory, the stability of a clay suspension depends on the net interaction energy between approaching particles, which is the sum of the repulsive double layer energy and the attractive van der Waals energy. When the net interaction energy includes a significant energy barrier, the suspension remains dispersed and stable, but when this barrier is eliminated or reduced, the particles can approach closely enough for the van der Waals attraction to cause them to aggregate. The practical manipulation of flocculation and dispersion is of great importance in industries that process clay minerals. In the ceramics industry, for example, it is often desirable to prepare highly concentrated clay suspensions, known as slips, that remain fluid and workable for extended periods. This is accomplished by adding dispersing agents, such as sodium silicate or sodium hexametaphosphate, which increase the surface charge of the clay particles and thereby increase the repulsive forces between them, preventing flocculation. Conversely, in water treatment applications, the goal is often to promote the flocculation and settling of suspended clay particles, which is accomplished by adding flocculants such as alum or polyacrylamide, which neutralize the surface charge of the particles and promote their aggregation into large, rapidly settling flocks. The thermal behavior of clay minerals is another area of considerable scientific and industrial significance. When clay minerals are heated, they undergo a series of structural transformations that are characteristic of their mineral type and that can be used for identification purposes. The first thermal event that is typically observed upon heating a clay mineral is the loss of adsorbed water, which occurs at temperatures below approximately 200 degrees Celsius and is accompanied by a broad endothermic peak in differential thermal analysis curves. For swelling clays such as montmorillonite, this stage may involve the loss of substantial amounts of interlayer water in addition to water adsorbed on external surfaces. At higher temperatures, typically between 400 and 700 degrees Celsius, depending on the mineral, the structural hydroxyl groups are driven off in a process known as dehydroxylation, which destroys the layer structure of the mineral and produces an amorphous or poorly crystalline residue. Further heating to still higher temperatures leads to the recrystallization of the amorphous material into new, high-temperature mineral phases, the identity of which depends on the chemical composition of the original clay mineral. The plasticity of clay, which is the property that allows it to be molded and shaped when moist, is perhaps the characteristic most closely associated with clay in the popular imagination. And it is the property that has made clay an indispensable material for human civilization since prehistoric times. The scientific understanding of plasticity in clays has advanced considerably over the past century, and it is now recognized that plasticity arises from a combination of factors, including the plate-like morphology of clay particles, which allows them to slide over one another when lubricated by thin films of water, the electrostatic and capillary forces that hold the particles together in a coherent mass, and the ability of the particles to orient themselves under stress. The Atterberg limits, developed by the Swedish soil scientist Albert Atterberg in the early 20th century and later standardized by Arthur Casagrande, provide a quantitative framework for characterizing the plasticity of clay soils. The liquid limit is defined as the moisture content at which a clay transitions from a plastic to a liquid state, while the plastic limit is the moisture content at which the clay transitions from a semi-solid to a plastic state. The difference between the liquid limit and the plastic limit is known as the plasticity index, and it provides a measure of the range of moisture contents over which the clay exhibits plastic behavior. The color of clay is determined primarily by its chemical composition, particularly the presence and oxidation state of iron. Clays that are rich in ferric iron, in which the iron is in the trivalent oxidation state, tend to be red, orange, or yellow, while clays that contain ferrous iron, in which the iron is in the divalent state, are typically green or blue-gray. White clays, such as pure kaolinite, owe their color to the absence of significant amounts of iron or other chromophore elements. The firing color of clay, which is the color that the clay assumes after being heated to high temperatures, may differ from the raw color because of changes in the oxidation state of iron and other chemical reactions that occur during firing. A clay that is gray in its raw state, for example, may fire to a red or buff color if the organic matter that causes the gray coloration is burned away and the iron is oxidized during firing in an oxygen-rich atmosphere. The use of clay in pottery and ceramics extends back to the earliest periods of human civilization, with the oldest known ceramic artifacts dating to approximately 29,000 years before the present. These earliest ceramics were not vessels, but figurines, such as the famous Venus of Dolní Věstonice, which was discovered in the Czech Republic and which was made from a mixture of clay and ground bone that was fired at a relatively low temperature. The development of pottery vessels, which revolutionized food storage and preparation, appears to have occurred independently in several parts of the world, with the earliest known examples dating to approximately 20,000 years ago in China and approximately 16,000 years ago in Japan. The types of clay used for pottery have varied widely across cultures and time periods, depending on what was locally available and what properties were desired in the finished product. Earthenware, which is fired at relatively low temperatures of approximately 900 to 1,150 degrees Celsius, can be made from a wide range of clay types and has been produced in virtually every culture that has practiced pottery. Stoneware, which is fired at higher temperatures of approximately 1,200 to 1,300 degrees Celsius, requires clays that can withstand these temperatures without excessive deformation, and it is characterized by a dense, vitrified body that is impervious to water even without glazing. Porcelain, the most refined of all ceramic types, is made from a mixture of kaolinite, feldspar, and quartz, and it is fired at temperatures of approximately 1260 to 1400 degrees Celsius, producing a translucent, glass-like body of exceptional hardness and beauty. The role of clay minerals in soil science is a subject of such breadth and depth that entire textbooks have been devoted to it. And yet even a brief survey of this topic reveals the extent to which the properties of clay minerals govern the behavior of soils in agriculture, hydrology, and engineering. The clay fraction of a soil, which by convention consists of particles smaller than 2 micrometers in diameter, typically accounts for between 10 and 60% of the total mass of the soil, depending on the parent material, the climate, and the degree of weathering. Despite constituting a variable proportion of the total soil mass, the clay fraction exerts a disproportionate influence on the physical and chemical properties of the soil, owing to the enormous surface area that these tiny particles collectively present. A single gram of montmorillonite, for example, can have an internal and external surface area of up to 800 square meters, which is roughly equivalent to the floor area of a moderately large house. It is on these vast mineral surfaces that many of the chemical reactions that govern soil fertility take place, including the absorption and release of plant nutrients, the buffering of soil pH, and the retention and movement of water. The ability of clay minerals to absorb and exchange cations is one of their most important properties from the perspective of soil fertility. The negatively charged surfaces of clay particles attract positively charged nutrient ions such as calcium, magnesium, potassium, and ammonium, holding them in a form that is not easily leached by percolating water, but that can be released to the soil solution when plant roots take up nutrients and thereby reduce the concentration of these ions in the immediate vicinity of the root surface. This process, known as cation exchange, is the primary mechanism by which soils supply many essential nutrients to plants, and the cation exchange capacity of a soil is widely regarded as one of the best single indicators of its inherent fertility. Soils with high cation exchange capacities, such as those containing abundant smectite or vermiculite, can retain large quantities of nutrient cations and release them gradually to meet plant demands, while soils with low cation exchange capacities, such as those dominated by kaolinite, are more susceptible to nutrient leaching and may require more frequent applications of fertilizer to maintain adequate nutrient levels. The influence of clay minerals on soil water retention is another aspect of their importance in agriculture and hydrology. The fine particle size and high surface area of clay minerals enable them to hold substantial quantities of water through a combination of adsorption on mineral surfaces and capillary retention in the small pores between particles. The relationship between soil water content and soil water potential, known as the soil moisture characteristic curve or water retention curve, is strongly influenced by the clay content and clay mineral type. Soils with high clay contents, and particularly those with abundant swelling clays, can hold more water at any given water potential than sandy or silted soils, but they also hold water more tightly, making it more difficult for plant roots to extract. The permanent wilting point, which is the soil water content below which plants can no longer extract sufficient water to prevent wilting, is typically higher in clay soils than in sandy soils, a consequence of the strong adsorptive forces that clay surfaces exert on water molecules. The engineering behavior of clay soils is a subject of particular concern in geotechnical engineering, where the properties of clay minerals can have significant consequences for the design and performance of foundations, embankments, retaining walls, and other civil engineering structures. The most problematic clay soils, from an engineering perspective, are those that contain significant proportions of smectite minerals, which can undergo large volume changes in response to changes in moisture content. As noted earlier, the annual cost of damage caused by expansive clays in the United States alone has been estimated at several $billion, making expansive soils one of the most costly natural hazards in the country. The identification and characterization of expansive soils typically involves a combination of mineralogical analysis, Atterberg limit determinations, and swell tests, in which undisturbed soil samples are placed in consolidation apparatus and their volume change upon wetting is measured under controlled conditions. The results of these tests are used to classify the swell potential of the soil and to guide the selection of appropriate foundation designs and construction techniques. The consolidation behavior of clay soils, which describes how they compress under sustained loading, is another property of great importance in geotechnical engineering. When a load is applied to a saturated clay soil, the load is initially carried by the pore water, which is relatively incompressible, and the excess pore water pressure that develops must dissipate by the gradual drainage of water from the soil before the load can be transferred to the soil skeleton. This process, known as primary consolidation, proceeds at a rate that depends on the permeability of the clay, the thickness of the clay layer, and the drainage conditions, and it can take months to years to complete in the case of thick, low permeability clay deposits. The theory of consolidation was developed by Carl Terzaghi, widely regarded as the father of soil mechanics, who published his groundbreaking work on the subject in the 1920s. Terzaghi's one-dimensional consolidation theory provides a mathematical framework for predicting the rate and magnitude of settlement under a given load, and it remains the foundation of consolidation analysis in geotechnical engineering practice to this day, although it has been extended and refined by numerous subsequent researchers. The permeability of clay soils to water is extremely low compared to that of sands and gravels, a consequence of the small pore sizes and the tortuous flow paths that characterize clay-rich materials. Typical values of hydraulic conductivity for compacted clay range from approximately 10 to the -7th to 10 to the -10th centimeters per second, which means that water moves through clay at rates that are many orders of magnitude slower than through sand, which typically has a hydraulic conductivity on the order of 10 to the -2nd to 10 to the -4th centimeters per second. This extremely low permeability makes compacted clay an ideal material for constructing barriers to prevent the movement of water and contaminants, and it is widely used in the construction of liners for landfills, impoundments, and other waste containment facilities. The effectiveness of clay liners depends not only on the permeability of the compacted clay, but also on the care with which the liner is constructed. Since even small defects such as desiccation cracks or poorly compacted seams can create preferential flow paths that dramatically increase the overall permeability of the barrier. The use of clay minerals in environmental remediation extends beyond the construction of physical barriers. The adsorptive properties of certain clay minerals, particularly smectites and modified clays, make them effective agents for removing contaminants from water and soil. Organically modified clays, known as organoclays, are produced by exchanging the inorganic interlayer cations of smectite with organic cations, typically quaternary ammonium compounds, which render the interlayer spaces hydrophobic and capable of adsorbing organic contaminants such as petroleum hydrocarbons, chlorinated solvents, and pesticides. The use of organoclays in permeable reactive barriers, which are installed in the path of contaminated groundwater plumes to intercept and remove contaminants as the water flows through, has been demonstrated in numerous field applications and represents a promising approach to the passive remediation of contaminated sites. The nanotechnology applications of clay minerals represent a rapidly growing area of research that has attracted considerable attention in recent years. The nanometer scale dimensions of clay mineral layers, combined with their high aspect ratio and their ability to be dispersed in polymer matrices, make them ideal candidates for use as reinforcing agents in polymer clay nanocomposites. These materials, which typically contain only 2 to 5% clay by weight, can exhibit significant improvements in mechanical strength, thermal stability, and barrier properties compared to the pure polymer. A result of the high surface area and the alignment of the clay layers within the polymer matrix. The preparation of polymer clay nanocomposites typically involves either the intercalation of polymer molecules into the interlayer spaces of the clay, resulting in an intercalated nanocomposite in which the clay layers are separated by a fixed distance, or the complete exfoliation of the clay layers, resulting in an exfoliated nanocomposite in which individual clay layers are uniformly dispersed throughout the polymer matrix. The latter configuration generally provides superior properties because of the greater interfacial area between the clay and the polymer, but it is more difficult to achieve and often requires careful control of the processing conditions and the use of compatibilizing agents. The pharmaceutical applications of clay minerals, while less widely publicized than their industrial and environmental applications, are nonetheless of considerable importance. Several clay minerals, including kaolinite, smectite, and palygorskite, have been used for centuries in traditional medicine as treatments for gastrointestinal disorders, and their use in modern pharmaceutical formulations continues to expand. Smectite, in particular, has been shown to be effective as an antidiarrheal agent, owing to its ability to adsorb toxins, bacteria, and viruses on its large surface area. And it is marketed under various brand names as an over-the-counter treatment for diarrhea in many countries. Kaolinite, similarly, has been used as an ingredient in anti-diarrheal preparations, although its effectiveness for this purpose has been the subject of some debate. In addition to their use as active pharmaceutical ingredients, clay minerals are also used extensively as excipients in pharmaceutical formulations, serving as binders, disintegrants, and controlled-release agents in tablet and capsule formulations. The agricultural applications of clay minerals extend beyond their natural role in soil fertility to include their deliberate use as soil amendments and animal feed additives. Bentonite is commonly added to sandy soils to improve their water and nutrient retention, and it is used as a binder in the production of animal feed pellets, where it helps to maintain the structural integrity of the pellets during handling and transport. Zeolites, which are crystalline aluminosilicates with structures that are related to those of clay minerals, are used as slow-release fertilizers, as soil conditioners, and as additives in animal feeds, where they have been shown to improve feed efficiency and to reduce the emission of ammonia from animal waste. The addition of small amounts of bentonite to poultry feed, for example, has been reported to improve the performance of broiler chickens, possibly by absorbing mycotoxins and other harmful substances in the digestive tract. The geological significance of clay minerals extends to their role as indicators of past environmental conditions, a field of study known as clay mineral paleoclimatology. Because the type of clay mineral that forms in a given environment depends on factors such as temperature, rainfall, drainage, and the composition of the parent material. The clay mineral assemblage preserved in a sedimentary sequence can provide valuable information about the climatic conditions that prevailed at the time the sediment was deposited. In general, kaolinite is associated with warm, humid climates with intense chemical weathering, while alite and chlorite are associated with cooler, drier climates or with physically weathered, unaltered source materials. Smectite, being typically associated with the weathering of volcanic materials under conditions of moderate drainage, can indicate the proximity of volcanic activity or the presence of alkaline, poorly drained conditions. By analyzing the clay mineral assemblages in cores of deep-sea sediment, which provide continuous records of sedimentation over millions of years, researchers have been able to reconstruct the climatic history of various regions of the world with considerable detail and precision. The identification of clay minerals in the laboratory is accomplished through a variety of analytical techniques, of which X-ray diffraction is the most widely used and the most definitive. In a typical X-ray diffraction analysis of clay minerals, a small amount of clay is separated from the bulk sample by sedimentation, deposited on a glass slide to produce an oriented mount in which the clay particles lie flat with their basal planes parallel to the slide surface, and then exposed to a beam of X-rays while the diffraction angle is systematically varied. The resulting diffraction pattern, which plots the intensity of the diffracted X-rays as a function of the diffraction angle, contains peaks at angles that correspond to the basal spacings of the clay minerals present, and the positions and intensities of these peaks allow the minerals to be identified and their relative proportions to be estimated. Additional treatments, such as saturation with ethylene glycol vapor and heating to 550 degrees Celsius, are routinely used to aid in the identification of swelling and non-swelling minerals. Because these treatments cause characteristic changes in the basal spacings of certain minerals that help to distinguish them from other minerals with similar untreated spacings. Other analytical techniques that are commonly used in the study of clay minerals include infrared spectroscopy, which provides information about the chemical bonds and functional groups present in the mineral. Scanning and transmission electron microscopy, which reveal the morphology and crystal structure of individual particles, and thermal analysis techniques, such as differential thermal analysis and thermogravimetric analysis, which characterize the thermal behavior of the mineral by measuring the heat flow and mass loss that occur upon heating. Each of these techniques provides complementary information that, when combined, allows a comprehensive characterization of the clay minerals present in a sample and their properties. The surface chemistry of clay minerals is a subject that has been investigated extensively using modern spectroscopic and computational methods, and these studies have revealed a level of complexity that was not fully appreciated in earlier decades. The surfaces of clay particles are not uniform but consist of basal surfaces, which are the flat faces of the layers, and edge surfaces, which are the broken edges of the layers where the crystal structure is terminated. The basal surfaces carry a permanent negative charge that arises from isomorphous substitution within the crystal lattice, while the edge surfaces carry a variable charge that depends on the pH of the surrounding solution, becoming more positive at low pH and more negative at high pH. This dual charge character means that clay particles can interact with both cationic and anionic species, and the relative importance of basal and edge interactions depends on the particle size and aspect ratio of the clay, the pH and ionic strength of the solution, and the nature of the species being adsorbed. The interaction of clay minerals with organic matter is a topic of considerable importance in soil science and environmental chemistry, because the clay-organic complexes that form in soils play a critical role in the stabilization and preservation of soil organic carbon. Organic molecules can be adsorbed on clay surfaces through a variety of mechanisms, including electrostatic attraction of positively charged organic species to the negatively charged basal surfaces, hydrogen bonding between organic functional groups and the hydroxyl groups on clay surfaces and edges, van der Waals interactions between organic molecules and the clay surface, and the intercalation of organic molecules into the interlayer spaces of swelling clays. The strength and reversibility of these interactions depend on the type of clay mineral, the nature of the organic molecule, and the physicochemical conditions of the environment, and they have important implications for the bioavailability and persistence of organic matter in soils and sediments. The global distribution of clay minerals in soils and sediments follows patterns that reflect the combined influence of climate, parent material, topography, vegetation, and time. In the tropical regions of the world, where temperatures are high and rainfall is abundant, the intense chemical weathering of rocks produces soils that are dominated by kaolinite and by iron and aluminum oxides, with little or no smectite or alite. These highly weathered soils, classified as oxisols and ultisols in the United States Department of Agriculture Soil Taxonomy, are characterized by low cation exchange capacities, low natural fertility, and a red or yellow color that reflects the abundance of iron oxides. In the temperate regions, where weathering is less intense, soils typically contain a mixture of alite, smectite, and vermiculite, along with lesser amounts of kaolinite and chlorite. And they tend to have higher cation exchange capacities and greater natural fertility than their tropical counterparts. In the arid and semi-arid regions, where the limited availability of water restricts chemical weathering, soils often contain significant proportions of unweathered primary minerals along with alite and smectite, and the clay mineral assemblage may closely resemble that of the parent material. The sediments that accumulate on the floors of the world's oceans provide a particularly comprehensive record of clay mineral distribution and transport. The clay minerals in marine sediments are derived primarily from the continents, transported to the ocean by rivers, wind, and glacial ice, and their distribution patterns reflect the source areas, transport pathways, and depositional environments that have characterized the ocean basins over millions of years. The Atlantic Ocean, for example, receives large inputs of alite and chlorite from the rivers and glaciers of North America and Europe, while the tropical Pacific receives relatively more kaolinite and smectite. The former from the deeply weathered soils of tropical land masses, and the latter from the alteration of volcanic materials on the seafloor and in island arc environments. The study of clay mineral distributions in marine sediments has contributed significantly to our understanding of oceanic circulation patterns, continental weathering histories, and the tectonic evolution of ocean basins. In bringing this extended examination of the properties of different clay types to a gradual and unhurried conclusion, it is worth reflecting on the remarkable diversity of properties that these seemingly simple minerals exhibit, and on the extraordinary range of natural and industrial processes in which they participate. From the kaolinite that lines the walls of a porcelain teacup to the bentonite that seals the borehole of an oil well, from the alite that anchors nutrients in the soil of a wheat field to the palygorskite that absorbs moisture in a container of cat litter, clay minerals touch nearly every aspect of human life, often in ways that go unnoticed and unappreciated. The study of these minerals, conducted patiently in laboratories and field stations around the world, continues to reveal new details of their structure, behavior, and applications, adding incrementally to a body of knowledge that has been accumulating for more than 2 centuries and that shows no signs of being completed anytime soon. And with that quiet observation, the discussion of clay minerals and their properties may be allowed to come to rest, leaving behind only the gentle impression of a subject that is, in its own unassuming way, both vast and deeply fundamental to the workings of the natural world. The investigation of clay mineral behavior under conditions of high pressure and temperature, such as those encountered in the deep subsurface of sedimentary basins, has been a productive area of research that has yielded insights of both scientific and economic significance. As sediments are buried to progressively greater depths, they are subjected to increasing temperatures and pressures that drive a series of mineralogical transformations collectively known as diagenesis. The diagenetic transformations of clay minerals are among the most important of these processes because they affect the porosity, permeability, and mechanical properties of the sediment, which in turn influence the migration and trapping of hydrocarbons, the behavior of faults and fractures, and the response of the sediment to tectonic forces. The smectite to alite transition, which was mentioned briefly in an earlier portion of this discussion, is perhaps the most thoroughly studied of all diagenetic clay mineral reactions, and the literature on this subject encompasses thousands of published papers spanning more than half a century of research. The kinetics of the smectite to alite transition have been investigated using a variety of approaches, including the analysis of natural samples from boreholes that penetrate sedimentary sequences of known age and burial history. Laboratory experiments in which smectite is reacted with potassium-bearing solutions at elevated temperatures, and theoretical models based on reaction rate theory and thermodynamic principles. The results of these studies have shown that the rate of the transition depends primarily on three factors: temperature, which provides the activation energy necessary for the reaction to proceed, the availability of potassium, which is required to replace the interlayer hydrated cations in smectite with the potassium ions that characterize alite, and time, which determines the extent to which the reaction progresses at any given temperature and potassium concentration. The activation energy of the smectite to alite transition has been estimated by various researchers to be in the range of approximately 80 to 130 kilojoules per mole, values that are consistent with the observation that the reaction proceeds slowly at temperatures below about 60 degrees Celsius, but becomes increasingly rapid at higher temperatures. The implications of the smectite to alite transition for the petroleum industry are manifold. The water that is released from the interlayer spaces of smectite as it converts to alite represents a significant source of fluid in the subsurface, and the timing and volume of this water release can influence the pressure regime of the basin and the migration of hydrocarbons. In some basins, the dewatering of smectite has been invoked as a possible mechanism for the development of overpressured zones, in which the fluid pressure exceeds the hydrostatic pressure expected at that depth, a condition that poses significant challenges for drilling operations and that must be carefully managed to prevent blowouts and other hazardous events. The conversion of smectite to alite also affects the sealing capacity of shales, because the elimination of the swelling interlayer spaces reduces the ability of the clay to self-seal fractures and other discontinuities, potentially increasing the permeability of the shale to fluids. This effect has important implications for the integrity of caprock seals that trap hydrocarbons in subsurface reservoirs, and it has been the subject of intensive research in the context of both conventional petroleum exploration and the geological storage of carbon dioxide. The behavior of clay minerals in the context of nuclear waste disposal is another area in which the properties of these minerals have significant practical implications. The disposal of high-level nuclear waste in deep geological repositories requires the construction of engineered barrier systems that can prevent the migration of radionuclides from the waste containers to the surrounding geosphere for periods of tens of thousands to hundreds of thousands of years. Compacted bentonite has been selected as the preferred buffer material for many proposed and operating geological repositories, owing to its extremely low permeability, its high swelling pressure, its ability to self-seal fractures, and its capacity to absorb and retard the migration of many radionuclide species. The performance of bentonite buffers under repository conditions, where temperatures may reach 100 to 150 degrees Celsius, and where the bentonite will be subjected to complex thermal, hydraulic, mechanical, and chemical processes simultaneously, has been the subject of extensive experimental and modeling studies. These studies have shown that while bentonite is generally well suited for this application, certain degradation processes, such as the transformation of montmorillonite to a light at elevated temperatures and the cementation of the bentonite by the precipitation of secondary minerals, could potentially compromise the long-term performance of the buffer if not adequately accounted for in the design. The relationship between clay minerals and the mechanical behavior of fault zones is a topic that has attracted increasing attention from structural geologists and seismologists in recent decades. Many of the world's major fault zones contain significant amounts of clay minerals, which are produced by the mechanical and chemical alteration of the rocks through which the fault passes. The presence of clay minerals in a fault zone can profoundly affect the frictional properties of the fault, because clay minerals generally have lower coefficients of friction than most other common rock-forming minerals. Montmorillonite, in particular, has an exceptionally low coefficient of friction, with values as low as 0.1 to 0.2 compared to values of 0.6 to 0.8 for quartz and feldspar, and its presence in a fault zone can significantly reduce the shear stress required for slip to occur. This observation has led to the hypothesis that the presence of clay minerals may explain why some faults appear to be weaker than would be expected based on laboratory measurements of rock friction, a phenomenon that has been particularly well documented in the case of the San Andreas Fault in California. The creep behavior of clay minerals, which refers to their tendency to deform slowly under sustained stress, is another property that has important implications for the long-term behavior of engineered structures and natural geological features. When a clay is subjected to a constant shear stress that is less than its peak strength, it will continue to deform slowly over time, a process that can lead to gradual movements of slopes, foundations, and retaining walls. The rate of creep depends on the stress level, the temperature, the moisture content, and the mineralogy of the clay, with smectite-rich clays generally exhibiting higher creep rates than kaolinite-rich or alite-rich clays. The mathematical description of creep in clays is typically based on empirical models that relate the creep strain to the logarithm of time, although more sophisticated models based on the theory of viscoplasticity have also been developed. The creep behavior of clay is of particular concern in the design of earth dams and embankments, where slow, progressive deformation can accumulate over decades and potentially lead to failure if not properly accounted for in the design. The electrical properties of clay minerals, while perhaps less immediately intuitive than their mechanical or chemical properties, are nonetheless of considerable scientific and practical interest. Clay minerals are electrical insulators in their dry state, but when wetted, they become conductive because of the mobility of ions in the diffuse double layer and in the pore water. The electrical conductivity of a clay water system depends on the concentration and mobility of the ions in solution, the surface charge density of the clay, and the geometric arrangement of the particles and pores. The measurement of electrical properties, particularly electrical resistivity and self-potential, is widely used in geophysical exploration as a means of mapping subsurface geological structures, identifying zones of contamination, and locating water-bearing formations. The distinctive electrical signature of clay-rich zones, which typically have lower resistivity than surrounding sandy or rocky formations, makes them readily identifiable in electrical resistivity surveys and well logs. The magnetic properties of clay minerals are determined primarily by the type and amount of iron present in their crystal structures. Most common clay minerals, including kaolinite, alite, and montmorillonite, are paramagnetic, meaning that they are weakly attracted by a magnetic field, but do not retain any magnetization after the field is removed. The paramagnetic susceptibility of these minerals is proportional to the amount of iron in the octahedral sheets and varies from mineral to mineral, with iron-rich varieties of chlorite and smectite generally exhibiting higher susceptibility than iron-poor varieties of kaolinite and alite. In addition to their paramagnetic properties, some clay-rich sediments contain trace amounts of iron oxide minerals, such as magnetite and hematite, which are ferromagnetic or ferrimagnetic and which can carry a natural remnant magnetization that records the direction and intensity of the Earth's magnetic field at the time the sediment was deposited. This property has been exploited extensively in paleomagnetic studies, where the magnetic record preserved in clay-rich sedimentary sequences has been used to reconstruct the history of geomagnetic field reversals, to correlate and date sedimentary strata, and to trace the past movements of tectonic plates. The optical properties of clay minerals, as observed under the polarizing microscope, are used routinely in petrographic studies to identify clay minerals in thin sections of rocks and sediments. Most clay minerals are so fine-grained that individual particles cannot be resolved under the optical microscope, and they appear instead as a diffuse, birefringent mass in which only the aggregate optical properties can be observed. However, some clay minerals, particularly those in the chlorite and mica groups, can form particles that are large enough to be identified by their optical properties, including their color, pleochroism, birefringence, and extinction angle. The optical identification of clay minerals in thin section is a useful reconnaissance technique, but it is generally insufficient for definitive identification, and it must be supplemented by X-ray diffraction or other analytical methods for a complete characterization. The role of clay minerals in the formation of ore deposits is a subject that has received considerable attention from economic geologists. Many types of ore deposits are associated with zones of intense clay mineral alteration, which form when hydrothermal fluids interact with the surrounding rocks and convert their primary minerals to clay minerals and other secondary phases. The type of clay mineral that forms depends on the temperature, pH, and composition of the hydrothermal fluid, as well as on the composition of the host rock. And the resulting alteration assemblage can provide valuable information about the conditions under which the ore deposit was formed. In porphyry copper deposits, for example, which are among the world's most important sources of copper and molybdenum, the ore is typically surrounded by a series of concentric alteration zones that include, from the center outward, a potassic zone characterized by biotite and potassium feldspar, a phyllic zone characterized by cerussite, which is a fine-grained white mica closely related to alite, a propylitic zone characterized by chlorite, epidote, and calcite, and an argillic zone characterized by kaolinite and montmorillonite. The recognition and mapping of these alteration zones, which can extend for kilometers beyond the visible limits of the ore, is an important tool in mineral exploration, because they provide a larger target for detection than the ore body itself and can guide the explorer toward the center of the hydrothermal system where the ore is most likely to be concentrated. The weathering of clay minerals themselves, although often overlooked in discussions that focus on the formation of clay minerals from the weathering of primary minerals, is a process of some importance in the long-term evolution of soils and landscapes. In highly weathered tropical soils, the clay fraction may consist predominantly of kaolinite and iron and aluminum oxides, reflecting the progressive loss of silica, alkali metals, and alkaline earth metals that occurs under conditions of intense leaching. Under the most extreme weathering conditions, even kaolinite may be unstable, and it can be dissolved and removed from the soil profile, leaving behind a residue composed almost entirely of aluminum hydroxide minerals such as gibbsite. These intensely weathered soils, known as laterites, can form thick crusts of iron and aluminum oxides that harden upon exposure to the atmosphere, a property that has made them useful as building materials in tropical regions for thousands of years. The formation of laterite involves the concentration of iron and aluminum by the removal of more soluble elements, a process that requires millions of years of sustained weathering under warm, humid conditions with good drainage. The study of clay minerals on other planetary bodies has emerged as an exciting frontier of clay science in recent decades, driven by advances in remote sensing technology and the exploration of Mars, the Moon, and other bodies in the solar system. The detection of clay minerals on the surface of Mars by orbiting spacecraft using infrared spectroscopy has been one of the most significant discoveries of the Mars exploration program, because the presence of clay minerals implies that liquid water was once present on the Martian surface in sufficient quantities and for sufficient durations to cause the chemical weathering of volcanic rocks. The clay minerals that have been identified on Mars include members of the smectite group, particularly nontronite, which is an iron-rich smectite, as well as kaolinite and chlorite. The distribution of these minerals across the Martian surface provides clues to the ancient hydrological history of the planet and has been used to identify locations where conditions may have been favorable for the development of microbial life. The Curiosity rover, which has been exploring Gale Crater since 2012, has detected clay minerals in the sedimentary rocks of the crater floor, confirming the orbital observations and providing detailed information about the mineralogy and chemistry of these ancient lacustrine deposits. The interaction of clay minerals with biological systems is a topic that spans the boundaries of geology, chemistry, and biology, and that has implications ranging from the practical to the philosophical. The hypothesis that clay minerals may have played a role in the origin of life on Earth, by serving as templates for the organization and polymerization of organic molecules, was proposed by the British chemist A. Graham Cairns-Smith in the 1960s, and has since been the subject of considerable theoretical and experimental investigation. According to this hypothesis, the regular, repeating structure of clay mineral surfaces could have provided a framework on which simple organic molecules were concentrated, organized, and linked together to form the more complex molecules that eventually gave rise to the first self-replicating systems. While this hypothesis remains speculative and is far from universally accepted, laboratory experiments have demonstrated that clay minerals can indeed catalyze certain organic reactions, including the polymerization of amino acids and nucleotides, under conditions that are thought to be representative of the early Earth environment. Whether or not clay minerals were directly involved in the origin of life, their importance in supporting and sustaining life through their role in soil fertility and nutrient cycling is beyond dispute, and their contribution to the habitability of the Earth's surface environment has been profound and continuous throughout the history of the biosphere. The industrial processing of clay minerals involves a series of operations that are designed to extract the clay from its natural deposit, purify it to the degree required for the intended application, and modify its properties as needed to optimize its performance. The specific processing steps vary depending on the type of clay, the nature of the deposit, and the end use, but a general sequence of operations might include mining, crushing, slurry preparation, classification, dewatering, drying, and grinding. In the case of kaolin, which is one of the most extensively processed of all clay minerals, the mining of primary deposits typically involves the use of high-pressure water jets, known as monitors, to wash the kaolin from the decomposed granite, producing a slurry that is then pumped to a processing plant for purification. The purification of kaolin slurry involves a series of steps that may include degridding to remove sand and other coarse particles, classification, using hydrocyclones or centrifuges to separate the clay into fractions of different particle sizes, magnetic separation, to remove iron-bearing minerals that would detract from the whiteness of the product, chemical bleaching, using reducing agents such as sodium dithionite, to convert ferric iron stains to soluble ferrous iron that can be washed away, and flotation, to remove titanium dioxide minerals and other contaminants. The processed kaolin is then dewatered, dried, and either shipped as a bulk powder or further processed by calcination to produce metakaolin, or by surface treatment with chemical agents to modify its surface properties for specific applications. The processing of bentonite is somewhat less complex than that of kaolin, but nonetheless involves several important steps. After mining, which is typically carried out by open-pit methods, the raw bentonite is crushed and dried to reduce its moisture content to a level suitable for further processing. The dried bentonite is then ground to the desired particle size and may be treated with sodium carbonate if the raw material is calcium bentonite that needs to be converted to sodium bentonite for applications requiring high swelling capacity. The quality control of bentonite products involves the measurement of properties such as swelling volume, viscosity, filtration loss, and gel strength, using standardized test methods developed by organizations such as the American Petroleum Institute. These tests ensure that the processed bentonite meets the specifications required for its intended application, whether that be drilling mud, foundry sand bonding, cat litter, or environmental sealing. The economic significance of the global clay minerals industry is considerable, although it often goes unrecognized because clay products are typically intermediate goods that are incorporated into a wide range of finished products rather than being sold directly to consumers. The global production of kaolin alone was estimated at approximately 37 million metric tons per year as of the early 2020s, with the largest producing countries being the United States, the United Kingdom, Germany, Brazil, and China. The global production of bentonite was estimated at approximately 20 million metric tons per year, with the United States, Turkey, India, Greece, and China being among the leading producers. The total value of the global clay minerals industry, including kaolin, bentonite, ball clay, fire clay, and other specialty clays, has been estimated at several $billion per year, making clay one of the more economically important categories of industrial minerals. The environmental considerations associated with the mining and processing of clay minerals are similar to those associated with other forms of surface mining and include the disturbance of land surfaces, the generation of waste materials, the consumption of water and energy, and the potential for air and water pollution. The mining of kaolin and bentonite typically involves the removal of overburden, which is the layer of soil and rock that overlies the clay deposit, and the excavation of the clay itself, both of which result in the creation of large open pits that must be reclaimed after mining is completed. The reclamation of mined lands typically involves the replacement of overburden, the regrading of surfaces to restore natural drainage patterns, the application of topsoil, and the establishment of vegetation. In many jurisdictions, mining companies are required by law to post bonds or provide other financial assurances to guarantee that reclamation will be carried out. And the mining of clay minerals is generally subject to the same environmental regulations that apply to other forms of mining. The water consumption associated with the processing of clay minerals can be substantial, particularly in the case of wet processing methods, such as those used for kaolin purification. The slurrying, classification, and dewatering steps all require significant quantities of water, and the management of process water, including its recycling and treatment before discharge, is an important operational and environmental concern. The energy consumption associated with clay processing is also significant, particularly in the drying and calcination steps, where large quantities of thermal energy are required to evaporate water and to drive the chemical transformations that occur at elevated temperatures. The carbon footprint of clay mineral processing is therefore non-trivial, and the industry has been increasingly focused on improving energy efficiency and reducing greenhouse gas emissions in response to growing concerns about climate change. The future of clay mineral science and technology is likely to be shaped by several converging trends, including the continued growth of nanotechnology applications, the increasing importance of environmental remediation and waste management, the expanding exploration of other planets, and the development of new analytical techniques that will allow clay minerals to be studied at ever finer scales of resolution. The application of clay minerals in nanotechnology is expected to grow as researchers develop new methods for exfoliating clay layers, functionalizing their surfaces, and incorporating them into polymer matrices and other composite materials. The use of clay minerals in environmental applications is likely to expand as the world faces growing challenges related to water pollution, soil contamination, and the management of hazardous and radioactive wastes. And the study of clay minerals on Mars and other planetary bodies will continue to provide new insights into the geological and potentially biological history of the solar system. The development of advanced characterization techniques, including synchrotron-based X-ray methods, neutron scattering, atomic force microscopy, and molecular dynamics simulations, has already revolutionized our understanding of clay mineral structure and behavior at the atomic and nanometer scales, and further advances in these and other techniques are likely to yield new discoveries in the years ahead. The ability to observe and model the behavior of individual clay layers and their interactions with water ions and organic molecules at the molecular level has provided insights that were simply inaccessible with the bulk analytical techniques that were available in earlier decades. And it has opened up new possibilities for the rational design of clay-based materials with tailored properties for specific applications. The cultural significance of clay, while tangential to the scientific discussion that has been the focus of this presentation, nonetheless deserves a brief mention, for it speaks to the deep and enduring relationship between human civilization and this most humble of earth materials. The word clay itself derives from the Old English cleig, which is related to similar words in other Germanic languages, and which reflects the importance of clay as a material in the daily life of the peoples who spoke these languages. The use of clay in pottery, as noted earlier, dates back tens of thousands of years, and the evolution of ceramic technology from simple, low-fired earthenware to the refined porcelains of China and Europe represents one of the great technological achievements of human history. The use of clay in writing, through the medium of cuneiform tablets, was central to the development of civilization in Mesopotamia, where records of trade, law, literature, and science were inscribed on clay tablets that have survived to the present day, providing an invaluable window into the intellectual life of ancient societies. The use of clay in construction, in the form of sun-dried and fired bricks, has been equally important in the development of human civilization. The earliest known bricks, dating to approximately 7,500 BC, were found at the site of Catalhoyuk in present-day Turkey, and the technology of brick-making has been practiced continuously since that time, making it one of the oldest surviving technologies in the world. The properties of clay that make it suitable for brick-making are its plasticity, which allows it to be molded into shape when wet, its strength when dried, and its ability to be further hardened and made durable by firing at elevated temperatures. The color and texture of fired bricks depend on the composition of the clay, the firing temperature, and the atmosphere in the kiln. And these variables have given rise to an extraordinary diversity of brick types that have been used in buildings ranging from humble dwellings to grand cathedrals. The medicinal use of clay, which was mentioned earlier in the context of pharmaceutical applications, also has deep historical roots. The ancient Egyptians used clay poultices to treat wounds and skin infections, and the Roman naturalist Pliny the Elder described the use of various types of clay for medicinal purposes in his Natural History, written in the 1st century of the Common Era. The practice of geophagy, or the deliberate consumption of earth or clay, has been documented in cultures around the world and is thought to serve a variety of purposes, including the detoxification of plant toxins, the supplementation of mineral nutrients, and the treatment of gastrointestinal disorders. Modern research has provided some support for these traditional practices, demonstrating that certain clay minerals can indeed absorb toxins and pathogens in the gastrointestinal tract, and that the mineral content of some clays could provide nutritional benefits, although the practice of geophagy also carries risks, including the ingestion of harmful contaminants and the impaction of clay in the intestines. The aesthetic appreciation of clay, as expressed in the art of ceramics, has a history that spans millennia and encompasses an extraordinary range of forms, techniques, and traditions. From the painted pottery of ancient Greece to the celadone glazes of Song Dynasty China, from the tile work of Islamic architecture to the studio pottery of modern craftspeople, the art of working with clay has been one of the most universal and enduring forms of human creative expression. The properties of different clay types, including their plasticity, their firing behavior, their color, and their response to glazes, have profoundly influenced the development of ceramic art. And the mastery of these properties has been the lifelong pursuit of potters and ceramists in every culture that has practiced the craft. The subtle variations in texture, color, and translucency that distinguish one type of clay body from another are appreciated by connoisseurs with the same discernment that wine enthusiasts bring to the evaluation of different grape varieties and terroirs. And the selection of the right clay for a particular purpose is considered one of the most fundamental skills of the ceramist's art. As this discussion draws to its gentle and unhurried close, it may be observed that the properties of different clay types, while they can be described in terms of crystal structures, chemical formulas, and physical measurements, are ultimately expressions of the deeper regularities of nature, in which the arrangement of atoms at the smallest scales gives rise to the behavior of materials at the scales that matter for human experience. The quiet precision of a kaolinite crystal, with its layers held in place by the steady pull of hydrogen bonds, the restless expansiveness of montmorillonite, always seeking to draw water into its interlayer spaces, the patient stability of a light, with its potassium ions snugly fitted into the hexagonal cavities of its tetrahedral sheets. All of these are manifestations of the same fundamental physical laws that govern the behavior of all matter, expressed in the particular idiom of the silicate minerals. And it is in the contemplation of these quiet regularities, in the slow accumulation of detail upon detail, measurement upon measurement, that the study of clay minerals finds its particular character, neither dramatic nor spectacular, but persistent, thorough, and deeply grounded in the patient observation of the natural world. With that reflection, this examination of the properties of different clay types may be allowed to come to its natural end, as gradually and imperceptibly as the weathering of a feldspar grain in a granite outcrop, a process that unfolds over millennia with the same quiet inevitability that has characterized every aspect of the story that has been told here. The specific gravity of clay minerals, which is the ratio of the density of the mineral to the density of water, varies within a relatively narrow range that reflects the similarities in their basic chemical composition and crystal structure. Kaolinite has a specific gravity of approximately 2.60 to 2.68, while montmorillonite has a specific gravity of approximately 2.35 to 2.70. Depending on the type and amount of interlayer cations and water. Elite has a specific gravity of approximately 2.60 to 2.90, and chlorite has a specific gravity of approximately 2.60 to 3.30. The wide range for chlorite reflecting the variability in the iron and magnesium content of different chlorite compositions. These values are generally lower than those of common non-clay minerals such as quartz, which has a specific gravity of 2.65, and feldspar, which has a specific gravity of approximately 2.55 to 2.76. But the differences are small and are not generally useful for separating clay minerals from non-clay minerals by gravity methods. The specific heat capacity of clay minerals, which determines the amount of thermal energy required to raise the temperature of a given mass of the material by 1 degree. is a property that has practical implications for the thermal behavior of soils and engineered clay barriers. The specific heat capacity of dry clay minerals is typically in the range of approximately 0.75 to 0.95 kilojoules per kilogram per degree Celsius, which is lower than the specific heat capacity of water, at 4.18 kilojoules per kilogram per degree Celsius, but comparable to that of most other common rock-forming minerals. When clay is wetted, however, its effective specific heat capacity increases substantially because of the contribution of the water that is adsorbed on and between the mineral layers. And this effect is particularly pronounced for swelling clays such as montmorillonite, which can hold large amounts of interlayer water. The thermal conductivity of clay, which determines the rate at which heat flows through the material, depends on the moisture content, the degree of compaction, and the mineralogy, with typical values for compacted clay ranging from approximately 0.7 to 1.8 watts per meter per degree Celsius. These thermal properties are important for the design of engineered clay barriers in nuclear waste repositories, where the clay must be able to dissipate the heat generated by the radioactive decay of the waste without reaching temperatures that could compromise its structural or chemical integrity. The compressibility of clay, which describes how much the material decreases in volume under applied pressure, is a property that has been studied extensively in geotechnical engineering because of its importance for predicting the settlement of foundations and other structures built on clay soils. The compressibility of clay depends on its stress history, its moisture content, and its mineralogy. Normally consolidated clays, which have never been subjected to effective stresses greater than their current overburden stress, are more compressible than overconsolidated clays, which have been subjected to higher effective stresses in the past and have therefore already undergone some degree of compression. The compression index, which is the slope of the void ratio versus the logarithm of effective stress curve in the normally consolidated range, is a commonly used parameter for characterizing the compressibility of clay, and it typically ranges from approximately 0.1 for stiff, low plasticity clays to more than 1.0 for soft, high plasticity clays. Montmorillonite-rich clays generally have higher compression indices than kaolinite-rich or aurite-rich clays, reflecting their higher water content and the greater deformability of the interlayer spaces. The shrinkage behavior of clay, which describes how the material decreases in volume as it dries, is closely related to its swelling behavior and is determined by the same mineralogical and structural factors. When a saturated clay is allowed to dry, it initially decreases in volume by an amount that is approximately equal to the volume of water lost, a stage known as normal shrinkage. As drying continues, the clay eventually reaches a moisture content at which the particles are in close contact and further water loss does not produce a corresponding decrease in volume, a state known as residual shrinkage. The moisture content at the transition between normal and residual shrinkage is known as the shrinkage limit, and it is one of the Atterberg limits that are used to characterize the behavior of clay soils. The shrinkage limit is typically lowest for smectite-rich clays, which can shrink to very low moisture contents before reaching the residual shrinkage stage, and highest for kaolinite-rich clays, which reach the residual stage at relatively high moisture contents. The volumetric shrinkage of clay upon drying can be very large, with some smectite-rich soils shrinking by as much as 30 to 50% of their wet volume, and the resulting shrinkage cracks can be several centimeters wide and extend to depths of a meter or more. These cracks have important implications for the hydrology of clay soils because they create preferential flow paths that allow water to bypass the clay matrix and move rapidly to depth, potentially carrying dissolved contaminants to the groundwater table. The anion exchange capacity of clay minerals, while generally much lower than the cation exchange capacity, is nonetheless a property of some importance in soil chemistry and environmental science. The positive charges on the edge surfaces of clay minerals, which arise from the protonation of exposed hydroxyl groups at low pH, can attract and hold negatively charged ions such as phosphate, sulfate, and nitrate. The anion exchange capacity is typically highest at low pH, where the edge surfaces carry the greatest positive charge, and it decreases as the pH increases and the edge surfaces become progressively more negatively charged. In highly weathered tropical soils, where the clay fraction consists predominantly of kaolinite and iron and aluminum oxides, the anion exchange capacity can be a significant fraction of the total ion exchange capacity, and it plays an important role in the retention of phosphate and other anionic nutrients. The adsorption of phosphate on clay surfaces is of particular agricultural importance because phosphate is an essential plant nutrient that is often in short supply in tropical soils, and the strong adsorption of phosphate on iron and aluminum oxide surfaces can render it unavailable to plants, a phenomenon known as phosphate fixation that is one of the principal limitations to crop production in many tropical regions. The acid-base properties of clay minerals, which are determined by the protonation and deprotonation reactions that occur on the mineral surfaces, play a fundamental role in controlling the pH and buffering capacity of soils and sediments. The basal surfaces of clay minerals carry a permanent negative charge that is independent of pH, while the edge surfaces carry a variable charge that depends on the pH, as described by surface complexation models. At the point of zero charge, which is the pH at which the net variable charge is zero, the edge surfaces carry equal numbers of positive and negative charges. The point of zero charge varies among different clay minerals, with typical values ranging from approximately pH 4 to 5 for kaolinite to approximately pH 6 to 7 for some iron-rich smectites. Below the point of zero charge, the edge surfaces carry a net positive charge, and above it, they carry a net negative charge. The buffering of soil pH by clay minerals occurs through the exchange of hydrogen ions and hydroxyl ions on these variable charge surfaces, as well as through the dissolution and precipitation of aluminum from the octahedral sheets of the clay minerals, which provides an additional mechanism of pH buffering at low pH values. The behavior of clay minerals in saline environments is a topic of considerable practical importance particularly in the context of agricultural irrigation with saline or sodic water, and in the drilling of oil and gas wells through formations containing saline pore waters. When the sodium content of the water in contact with a smectite clay exceeds a certain threshold relative to the calcium and magnesium content, the interlayer cations become predominantly sodium, and the clay exhibits its maximum swelling behavior. In agricultural soils, this condition, known as sidicity, can lead to the dispersion of clay particles, the destruction of soil structure, the clogging of pores, and a dramatic reduction in the permeability of the soil, making it difficult for water to infiltrate and for roots to penetrate. The management of sodic soils typically involves the application of gypsum, which provides a source of calcium that can replace the sodium in the interlayer spaces and on the exchange sites of the clay, thereby reducing the swelling and dispersion and improving the physical properties of the soil. The sodium adsorption ratio, which is the ratio of the sodium concentration to the square root of the average concentration of calcium and magnesium in the irrigation water, is widely used as an indicator of the sidicity hazard of irrigation water, and guidelines for the safe use of saline and sodic water in irrigation have been developed by organizations such as the Food and Agriculture Organization of the United Nations and the United States Salinity Laboratory. The freeze-thaw behavior of clay soils is a property of significant importance in cold regions, where the repeated freezing and thawing of soil water can cause substantial damage to roads, foundations, and other infrastructure. When water in clay soil freezes, it forms ice lenses that grow by drawing additional water from the surrounding unfrozen soil through a process known as cryosuction. The growth of these ice lenses causes the soil to heave upward, and when the ice melts in spring, the soil settles back, often unevenly, resulting in the characteristic frost heave damage that is observed on roads and sidewalks in cold climates. The susceptibility of a clay soil to frost heave depends on its permeability, its capillarity, and the rate of freezing, with silted clays generally being more susceptible than pure clays because their moderate permeability allows water to be drawn to the freezing front more readily. The depth of frost penetration in a given location depends on the air temperature, the snow cover, and the thermal properties of the soil, and it can range from less than a meter in temperate coastal areas to several meters in continental subarctic regions. The acoustic properties of clay, including the speed of sound and the attenuation of acoustic waves, are relevant to geophysical exploration techniques, such as seismic reflection and acoustic logging, which are used extensively in the petroleum industry to characterize subsurface geological formations. The speed of compressional waves in saturated clay typically ranges from approximately 1,500 to 2,500 meters per second, depending on the porosity, the effective stress, and the clay mineral content. The speed of shear waves in clay is generally lower than the speed of compressional waves, with typical values ranging from approximately 100 to 600 meters per second. The ratio of compressional wave speed to shear wave speed, known as the VP/versus ratio, is often higher in clay-rich sediments than in sandy sediments, and this difference can be used to distinguish between clay-rich and sand-rich zones in seismic data. The attenuation of acoustic waves in clay is generally higher than in sand or rock, owing to the viscous dissipation of energy in the pore water and the frictional interactions between clay particles. And this attenuation can complicate the interpretation of seismic data in areas where thick clay sequences are present. And so the examination of the properties of different clay types arrives at its final resting place, having traversed a landscape of scientific detail that stretches from the atomic scale of crystal lattices to the planetary scale of Mars exploration. From the ancient art of pottery to the modern science of nanotechnology, and from the practical concerns of agriculture and engineering to the philosophical speculations about the origins of life itself. Throughout this journey, the guiding theme has been the remarkable diversity of properties that clay minerals exhibit, a diversity that arises from relatively simple variations in crystal structure and chemical composition, but that manifests in an extraordinarily wide range of physical, chemical, and mechanical behaviors. The study of these properties, pursued with quiet diligence by generations of scientists in laboratories and field stations around the world, has produced a body of knowledge that is both deep and broad. And that continues to grow as new questions are asked and new tools are brought to bear on old problems. In the end, it is perhaps the very ordinariness of clay, its ubiquity in the natural environment, and its familiarity in everyday life that makes the scientific study of its properties so quietly satisfying. For it reveals that even the most commonplace materials, when examined with sufficient care and attention, can yield insights of surprising depth and beauty.